While I'm waiting for everybody else to log in, anybody have questions left over from Tuesday? Not that we covered a vast amount of information on Tuesday, other than the syllabus. And I also have it recording tonight, which I didn't have it set up for on Tuesday, so hopefully I've fixed it so that it automatically starts that. I think I'm still missing 3 people from my roll list. I'm playing musical locations this week since Tuesday was in my office, which is down in the Hilltop area. And then last night I went over to campus so I could do a couple of odds and ends in lab. And then tonight I'm actually home so you can see all the stuff behind me. All right, let us dive back into some more organic chemistry. So toward the end of Tuesday, we began to talk a little bit about functional groups. And we did talk a little bit about the alkanes here. The alkanes being basically the simplest of the organic compound groups based upon what they're made of and how they're arranged. So the alkanes being the ones that only have hydrogen and carbon and also have only single bonds. So I gave you here a handful of some of these smaller ones that fall into this category. Ones with 1, 2, 3, and 4 carbon atoms. And then we talked just a little bit at the very end of class about the naming system. And this will kind of come back around as we progress through the chapter and then kind of return to some of the naming again. So unfortunately, the overwhelming majority of the things that go into naming organic molecules have little to nothing to do with the inorganic nomenclature that you learn in first semester. Actually, I'm like having an oddball problem here with my volume. All right, let me try this. Okay, hopefully that's better. So as you're doing nomenclature, it really depends a great deal upon how many carbon atoms are in your molecule. If you start at the lowest possible end, being 1, they have a prefix system that's being used here that begins with meth. Methane being the first one in this particular set because the ANE ending is part of your indication that you are dealing with an alkane molecule. We have eth, prop, and bute for 2, 3, and 4. And then we do actually return to prefixes, which did get used kind of both from a geometry point of view, and they are used to some degree in the naming of the nonmetals in the inorganic nomenclature end of things. So pent, hex, hept, oct, none, and dec. And yes, there are prefixes for things that are bigger than 10, but we're not super interested in that for the purposes of this class. And then I think the final thing that I ended with on Tuesday was to mention what happens when they burn. Okay, combustion being burning, and you get primarily, not exclusively, carbon dioxide and water as the combustion products. All right, let's make this one notch different. If you take the same hydrogens and carbons that were used in making the alkanes, but you insert a double bond, those then become known as the alkenes, spelled almost the same way, change a vowel. So these all end in ene. If you look at the handful that I dug up there, note there are no one carbon alkenes. You can't have a double bond if you've only got one carbon. So the bottom end of the alkenes starts with 2 carbons. So we have ethene, propene, butene, pentene. These having the same prefixes that you saw for the alkanes. We're not using the meth because that would imply that we only had a single carbon. Note that each of those molecules pictured has a double bond. However, this is also somewhat of an incomplete picture in that we could put those double bonds, once we get to butene and pentene, we could put double bonds in different spots in the molecule. So that will kind of come back again as we sort of dive more into nomenclature when we get through the functional groups, is you will see that there are some additional pieces of information that you might see used to indicate where in the molecule the double bond occurs. So let me show you on my Tinker Toy things here. So I built an ethene. Okay, let me kind of tip it over here. You can see the double bond. I've got the two little curved pieces of plastic here that represent the double bond. If I turn it back sort of right side up here and tip it a little bit so you can kind of see the ring there. We've got 2 carbon atoms. You have 2 hydrogens on each end. You don't have 6 hydrogens because even though carbon wants 4 bonds, if we look at the one here, we've got 1, 2, and then 3, 4 are your 2 hydrogens. And you obviously have a mirror image here on the other end. So this kind of gives you, it still gives you 4 bonds for each of the 2 carbon atoms there, but 2 of those bonds are to each other. So this gives you kind of a little bit of extra dynamic about how your molecule is put together. All right, next variation. What if instead of a double bond, you have a triple bond, reminding you that there are no quadruple bonds in organic chemistry. There is no physically possible way to put 4 pairs of electrons, which would actually be 8 electrons, all between just 2 atoms. You max out when you have a triple bond because that represents 6 electrons, holdovers from some of the information covered in Lewis structures in first semester chemistry. So let me scroll down a little bit here. This one kind of gives you the same basic premise. We've got 2, 3, 4, 5, and actually there is a molecule here that shows you 6 carbons. Note, we are still using the same prefixes, eth, prop, bute, pent, hex. Change your vowel again. Well, I guess Y is sort of a vowel. And all of these have a name that end in YNE. Again, this is clues that you have at least one triple bond involved in the molecule. We also begin to see a couple variations on structure here. And this is something that we will not only sort of continue through this chapter, but you'll also see it in the organic lab that we will be doing in about 2 weeks on Zoom. In that open structure, or sometimes referred to as expanded structure, is very specific in that it shows you every single bond that is present and every single atom that is present. And granted, it is space hogging in that it takes up more space to write these out on a sheet of paper because you are showing all this information. Condensed structure, note, the biggest difference here is it doesn't show you the legs where the hydrogens are attached. Yes, it tells you how many hydrogens there are, but it doesn't show you the stick that represents the bond between the carbon and however many hydrogens it happens to have. So one of the benefits of a condensed structure, as you're sort of progressing through organic chemistry ideas, is that it is a little bit simpler to write in terms of space saving. It's also easier to type for purposes of like me creating notes and things like that. I don't have to put as many kind of separate lines in when I'm drawing out where all the hydrogens are. However, there is one more version. Okay. You will also sometimes see these, okay, whereas this one was called condensed at the top, there is one that I will kind of loosely refer to as ultra condensed. The further you get in chemistry, general chem being kind of the base classes, organic being kind of the next layer, by the time you hit biochemistry, and in fact, in some of the upper levels of organic, it becomes kind of shapes. So if you look at the one labeled limonene there on the left-hand side, the hexagon is a way to represent that there are 6 carbons in a hexagonal shape. You'll note there's one little extra dash slash up there in kind of the upper half of that hexagon, which is a way of indicating that there is a double bond present between those 2 corners. The bottom end looks like it has one leg on kind of the left-hand side of the bottom of that molecule, and it kind of looks like it has 2 spider legs on the right-hand side there. Again, this is kind of a shorthand way of indicating to you that you have a single bond on the left-hand bottom edge of that molecule, but a double bond on the right-hand side. I have to show you something because it is sort of tangentially related. Not that this is a molecule, but this is a bacteriophage. Note it has legs on the bottom. If you've taken college level biology, you may be familiar with what a bacteriophage is. And I actually think the molecule there looks a great deal like a bacteriophage. So I was kind of amused when I ended up picking that molecule for my example. It was sort of coincidental. So look at the one next to it called terpenine. So we have a similar molecule, has a hexagonally shaped carbon ring at the top that contains two double bonds that are on opposite sides from each other. It doesn't have any double bonds on the lower portions that are poking out the bottom, the 6 o'clock position of that molecule. So it's related, and yet it's a different molecule. It has double bonds in some different places. And then I picked one somewhat more extensive molecule that still uses the same basic notation. Every corner is a carbon, and you are supposed to assume that every carbon has an appropriate number of hydrogens so that it has 4 bonds. Beta carotene, the stuff that's literally in your carrots, this is what makes them orange. This is a long molecule that is predominantly just carbons and hydrogens, but note there are some ring structures and there's quite a number of double bonds that all occur in this molecule, and it gives it a particular shape. So these are things that you will kind of see intermittently interspersed as we sort of continue through this chapter. Is there's the expanded version, which shows you every carbon and every hydrogen with appropriate sticks. There's a sort of semi-condensed version, which does tell you how many hydrogens there are, but doesn't draw them poking out like spokes. And then there is this more ultra-condensed version, which has its uses, but we're probably not going to see a huge amount of. This is also sometimes referred to as a skeletal form. As I said, upper levels of organic chemistry as well as biochemistry uses this kind of notation extensively. All right, so those are the first 3 functional groups: alkanes, alkenes, alkynes. We still have one more group that is limited to just carbons and hydrogens. And I know a few of you had me last semester, and we talked a little bit about benzene, and benzene being a fascinating molecule in terms of resonance. It is a hexagonal molecule composed of 6 carbons and 6 hydrogens, but it also has alternating double bonds. So the first of the pairs of molecules written here at the bottom of this page shows you the 2 alternate versions. Now note, they're very, very similar. But if you look at the left-hand one, its double bonds, of which there are 3, are at roughly 11 o'clock, 3 o'clock, and about 7 o'clock on the molecule. Its alternate form didn't change where the carbons are, didn't change where the hydrogens are, but I rotated where my double bonds are. All of them flopped over one spot around the hexagon. So you have a double bond at roughly 2 o'clock, one at about 5 o'clock, and one at about 9 o'clock. So here are some other alternate ways you will see this drawn. Okay. Sometimes they just draw the hexagon with the 3 dashes all appropriately spaced apart. Sometimes they will just literally draw the hexagon with a circle in the middle. This is a very, very shorthand way to draw benzene. And then the picture that I grabbed off the net just kind of gives you the expanded version there on the right-hand side. So you have a way to compare how all 3 versions of the same molecule are actually drawn. So why are we interested? One, this is an important structure in terms of organic chemistry. It, like the alkenes and the alkynes, is considered to be unsaturated, meaning that I have the potential to break double bonds and put more hydrogens in so that all of my carbons stay happy with their 4 bonds. But it also has this fascinating resonance structure that is unbelievably stable. So look at the little orange coded picture there. Once you have the 6 carbons all in their little hexagon, and you have to think back to orbital ideas here. Remember that there are s orbitals, p orbitals, d's and f's, but carbon only has s's and p's. So if you stick all of your carbons in a ring, what happens is, since the p orbitals are oriented in such a way that half of that lobe is poking upward and half of it is poking downward, you get this thing that they sometimes refer to as delocalization. You get this smear of electron cloud that is basically circular above and below the plane of the hexagon. So assuming your hexagon is flat, you have this circular racetrack above and this sort of circular racetrack below as your double bonds go floppity, floppity, floppity and migrate around the ring kind of sequentially, is what I would say. So things to think about that are all influencing how the benzene behaves. Now, things that are true also about benzene is it is unbelievably stable. You would think that it would be kind of fragile, that once you stick these 4 or 6 carbons in a ring, that if you torque them or bent them, that they would fall apart easily, which is actually not true. They're very, very stable. Let me go back to the concept of unsaturated here for a moment. So let me scroll back up. So we looked at our alkenes. If you broke the double bond, you could add more hydrogens into where you broke that double bond. You could add 2 additional hydrogens. The same is basically true of the triple bond. You could break both of those additional bonds and add 4 more hydrogens. So because you have the ability to add additional hydrogens, this is one of the reasons why they are referred to as unsaturated. So little real world input here. So when people talk about saturated fats in terms of like butter, lard, Crisco, all of those are situations where the hydrogen carbon chain has no double bonds. In fact, if you have soybean oil, it usually has at least 1 or more double bond, which is part of what allows it to be an oil at room temperature. But if you want to take your soybean oil and make Crisco, you have what is known as partially hydrogenated soybean oil, which basically means they broke some of those double bonds and inserted extra hydrogens, which then means your substance is less liquidy at room temperature and more solid at room temperature. So all of those are kind of a little bit of things that have a little bit of real world relevance that outside of the chemistry classroom. Something that is not well covered by your book is the concept of isomers. I cover it in lecture. We also see some of it in the lab that is upcoming. One of the things that's true about organic chemistry is a lot of times you can take the same number of atoms and rearrange them in different ways. So these are referred to as isomers. They have identical composition, but if you build them, they look different. We're going to take a look at the ones that are referred to as structural isomers. We're also going to look at the stereoisomers and geometric isomers a little bit. And I realized I have see my little red squiggly line here, and it means I spelled composition wrong. So one of the bottom end ones that's kind of easy to look at here. If you take 2 carbons, 6 hydrogens, and a single oxygen, there's a couple of different ways you can arrange this. And I use the kind of condensed notation to show this here on kind of the middle of the page. We've got CH3, CH2 with an OH on the right-hand end of that string. This is an ethanol molecule. Ethanol being like what's in your beer. On the other hand, same number of atoms. We're going to take the oxygen molecule, and instead of kind of dangling it out close to the end, we're going to stick it dead center in the molecule. And you'll have a left-hand carbon with its accompanying 3 hydrogens, and a right-hand carbon with its accompanying 3 hydrogens. And my oxygen's in the middle. This is known as dimethyl ether. This is a cousin of the ether that once upon a time used to be used as a general anesthetic in surgery in the early 1900s. Because before the 1900s, your options for anesthetic usually involved either bite on the stick or here's a fifth of whatever liquor you prefer and drink it as fast as you can, and hopefully you'll be so drunk you won't notice we're doing surgery on you. The advent of ether as a usable compound was kind of a big deal. So look at not only the way the molecules are drawn, which are different. Look at the BP for boiling point, MP for melting point. Note they have relatively different values. Boiling point for ethanol is actually lower than the boiling point of water because these are in Celsius. Boiling point of ethanol is 78.5. Okay, this is actually why when you distill alcohol, the alcohol comes through the still first, and a lot of the watery leftovers are left in the original container because water boils at 100 and ethanol boils about 20 some degrees lower. So this is one of the things that allows you to distill alcohol and purify it. Note that your melting point is actually negative, okay? negative 117 Celsius. Now look at the one for ether. We've got a much lower boiling point here. We've got a negative boiling point. Boiling point of negative 25 means if you had a bottle of dimethyl ether and you left the cap off, if you came back in a couple of hours, a substantial portion of it would have evaporated. Note, the melting point is also lower, okay, as well as the boiling point being lower. The melting point is not quite 20, and quite a full 20 degrees lower at a negative 138.5. So not only did we get a different looking molecule, it affects their physical characteristics, their physical properties, things that could be measured in a laboratory situation. All right, let's take a look at something which only involves hydrogens and carbons. C4H10. Well, if you want to take those 4 carbons and their 10 accompanying hydrogens, one way is to make it a long string. Hook them all together. You will sometimes see this also referred to as N as in Nancy, butane. However, the N in organic chemistry loosely refers to the word normal, which in the world of organic chemistry means it's a string, as opposed to the other molecule beside it, exact same number of atoms, but it's called isobutane. I've got my 4 carbons, but they're in more kind of a T shape. 3 of them are in a chain, but one of them kind of dangles from the center. Again, you still have your 10 hydrogens. They're all there and accounted for. We just arranged it differently. Here's another thing you're going to run into. We're going to try to predominantly stick to the IUPAC naming system. Remember back in first semester, there were 2 naming systems for the inorganic world. There were things like you could call things by their like chromus and chromic versus chromium 2 and chromium 3. There was mercurous and mercuric. One of them being the stock system, which used the Roman numerals, and the other one loosely were being referred to as the older naming system. Well, in the world of organic chemistry, it's not a whole lot of different. There's the IUPAC system, but then there's an older system, which gets used quite a bit, especially in the world of medicine. They use some different prefixes, and they have some other variations thrown in, like sec and ISO and some other odds and ends. So we're going to run across those a little bit. If you are hunting around for additional examples on websites, be aware that you may see some of these variants, because websites often don't differentiate as to which ones are IUPAC system and which ones are the older system. How about 5 carbons? So the more carbons you have, the more options you get. I only had 2 versions when I did the butane. There's the long string, or there's kind of T-shaped. If I throw an additional carbon in, I've got the straight version. I've got 2-methylbutane, which is similar to the isobutane, but there's 4 in the chain, and then there's this one dangling bit. I've also got one that's referred to as 2,2-dimethylpropane, which doesn't sound like it should have 5 carbons at all, but it does. We're going to talk more about the naming rules maybe at the end of today, but also probably more likely Tuesday. My string going horizontally had 3 carbons in it, which is why they loosely refer to that as a propane. But it has 1 twig upward and 1 twig downward. And this is where you get all 5 of your carbons combined into this molecule. Literally, the more carbons you have, the more isomers. Once you get up to 6, 7, 8, 9, 10 carbons, you have quite a bit more isomers that could be constructed. All right, now on to the stereoisomers. So let me go back to my Tinker Toy. I'm going to show you pictures, and then I'm going to show you my Tinker Toy. So the geometric ones are based upon the idea that if you have a double bond, the double bond does not rotate anywhere with near the same ease that a single bond would. So this is going to impact how you put your molecules together. As I grab molecules here to show you a little bit more about the rotation end of things. All right. 2 carbons, 3 hydrogens on each end, single bond. Watch me twist it. And it is literally capable of doing this, okay? Granted, it's on a more fuzzy level because we're talking about electrons, but the rotation is completely possible, okay? This gives you the ability to twist and turn. If you had a long chain, you can twist it and turn it in a whole bunch of different ways without actually changing the molecule. It just has to do with the rotational energy is what they call it. So here's my molecule with a double bond, and I put different colors on so they're a little more obvious here. If this is, let's say it's a CH3 up here that's green, and I've got another one down here. Note, my double bond doesn't rotate, okay? It's really rigid. So building my molecule this way, where my things that match are on opposite sides, is actually a different molecule than if I swivel it around here a little bit and make my 2 things that match actually poking in the same direction. These are known as cis and trans isomers. You have to have a double bond. You have to have 2 things that match. Cis means same in Latin. I think it's Latin. Trans means different. So as in like transatlantic flights, okay, you are going across to a different place, okay? But the trans is sort of more literally, I guess on a more literal translation is more of an across and a little bit less of a different. When you have a cis molecule, your 2 matching items are on the same side of the double bond. If you have a trans molecule, your 2 matching items are on the opposite sides of your double bond. More real world stuff. When you buy your Oreo packages these days, and they now announce contains no trans fats, and people go, oh, okay, I know trans fats are supposedly bad, but I have no idea why. Okay. Part of it has to do with this kind of geometry. If your long, flexible hydrogen and carbon chain that has a double bond or two in it contains cis-oriented double bonds, your body thinks that's cool and processes them. Yes, it's still a fat, but it processes them in ways that are actually designed for your body to use. Trans fats are artificial. Trans fats happen. Remember that partially hydrogenated soybean oil thing? So trans fats don't happen in nature. Trans is something that happens when humans do things to molecules to create double bonds in weird places that are not oriented in the same-sided direction that normal ones are. If you butter, lard, all of those things that are naturally occurring fat products, they only have cis double bonds for the double bonds they do have. They don't have any trans. Crisco, on the other hand, is capable of having trans fats because of the way it's created. So not only are they unsaturated, it makes a difference how they are structured. And it really is all about the lack of rotation. And I realized that I did not put my picture of optical stuff in here. I was putting images in this so that I can, do it here on Zoom. And I realized I don't have my optical thing. All right. Let me see if I can use my whiteboard to do this. All right. Optical isomers are about what is sometimes referred to as handedness. Okay. In biology, they call them DNL. In chemistry, if you take lots more organic chemistry than the small amount that we are covering, you will see them referred to as RNS. All right. Let's see if I can draw this the way I would like to. All right. We're going to have carbon. And we're going to put 4 different items on this carbon. We're going to put a Cl and an F and a bromine. Yeah, I know this is a bizarre looking molecule. And a CH3 down here at the bottom. All right. That's one version of this molecule. My sort of straight line that's down the middle there is a mirror. You can have this same molecule, and I'm going to leave my Cl and my CH3 in the same spot. But this time around, I'm going to put my fluorine on the right-hand side. Oops. And my bromine on the left-hand side. Okay, why does it make a difference? So in the world of biology, handedness, like the whole cis and trans thing, makes an unbelievably big difference. So glucose used by your body comes in two versions, of which they're a little bit more involved in this particular molecule, but I'm using this molecule as kind of a way to show you the handedness idea. Glucose is, in the world of organic chemistry, available in a D version and an L version. So D-glucose is not processable by the human body. So if you take D-glucose and you combine it with some fructose, you basically get Splenda, which is a sucrose molecule that contains an item that your body can taste but doesn't process. So if you have L-glucose, your body thinks, cool, okay, I can use this. If you've got D-glucose, it can't use it. So because these are mirror images, and your little enzymes can tell the difference, it makes a very big difference in the world of biology. So think about it this way, okay? You have two hands, okay, which are mirror images of each other, more or less. So I can fold them in half, and obviously they match up if I fold them across. But if I do this, okay, if I sit one hand on top of each other, okay, my thumbs are on the opposite sides, okay? My thumbs don't match, and my pinkies don't match, okay? And that's kind of the situation that's going on when you have DNL/RNS types of optical isomers. We just kind of mentioned this in passing, and you'll see just a little smidge of it get mentioned once or twice more in the semester. So we just sort of introduce it so that you have heard this information. The cis and trans is more important in terms of being able to recognize it and or draw it. So let me go back to my other stuff here. So we've got these two different kinds of isomers. We've got the geometric ones, we've got the optical ones, we've got the structural ones, which are about literally popping the molecule apart and putting it back together a different way. Isn't organic chemistry interesting? You're either thinking, oh, cool, it's pictures, or you're about ready to tear your hair out. So we're gonna do a few more functional groups tonight. We are done temporarily with the ones that only contain carbons and hydrogens. So we're going to add this additional atom to the picture. We're going to add some oxygens. So if you have some kind of a chain, your chain can be literally as small as a single carbon, or it can be much longer. But as long as there is an OH, an oxygen with the hydrogen on its outside edge, you have an alcohol. R is considered to be shorthand. R is a generic way of saying, oh, there's just some carbons and hydrogens here. So methanol, wood alcohol, which kills off your retinal cells if you drink it, is a single carbon atom with 3 hydrogens and 1 OH. If you add an additional carbon, now you get ethanol, component of your beer. It still has that OH on the end. And I found this nice picture that I like that shows you that there are some other variations on a theme. So one of the things that sort of happens as you sort of look across from left to right across that lower picture there that has N-propyl, isopropyl, cyclohexanol, isobutyl, and tert-amyl is how many things are attached to the carbon with your OH. If all you have is a chain, they will often refer to this as a primary alcohol. You recognizing that it's an alcohol is the key function there. But again, some of this is about exposure. Isopropyl alcohol, and if you look at the slightly more expanded version up above there as opposed to the stick version, you can see there's a CH in the middle, there's a CH3 on the left and on the right, and your OH is actually in the middle. So if you compare the first left-hand molecule there, the N-propyl one, it's actually still got all the same stuff. It's got 3 carbons and it's got an appropriate number of hydrogens and it has a single oxygen. It's an isomer. But N-propyl alcohol is not only expensive, it's harder to make. So if you buy alcohol at the drugstore, not the kind you drink because you would not want to drink this, the kind where if you're gonna clean off grease from your face, or if you want to give yourself an injection or something like that, the alcohol that's used for medical purposes, it's isopropyl alcohol. There is a difference. What if I had a ring? Now, granted, it's not a benzene ring. Cyclohexanol. 6 little carbons in a ring, no double bonds, but does have an OH dangling off to one side. It's a secondary alcohol. That little carbon that has the OH is hooked to 2 other carbons. Then we keep going we're going left to right here. Isobutyl alcohol. Okay, it has 4 carbons and all its appropriate numbers of hydrogens, but the OH is kind of out on the far right-hand end. So it's a primary alcohol. What if it was kind of balled up? The last one on the right-hand side there, and again, this is one of these things where it's giving you a old name. Tert-amyl alcohol is the old naming system. 2-methyl-2-butanol is the IUPAC system. Again, you're not going to have to name things that are not carbons and hydrogens alone, but we're trying to kind of introduce you to the ideas. For that one's called a tertiary alcohol. That carbon where the OH is attached has one pointing up carbon group, one left-hand pointing carbon group, and one downward pointing carbon group that are all attached to the same C as the OH. This is why it's called a tertiary alcohol. So alcohols come in various versions. The big take home to this is they have to have an OH poking outward, attached to the other stuff. Next one. This is probably going to be the last one we cover tonight. Ethers. Okay, we a little bit earlier looked at some dimethyl ether, and one of the things that I pointed out was, ooh, the oxygen is in the middle. This is a key feature of what makes an ether an ether. So diethyl ether. This is the one that they used to use for general anesthetic purposes. diethyl ether, or sometimes it's called ethoxyethane if you're doing the IUPAC thing. Medical people just tend to call it diethyl ether. One of the downsides to diethyl ether is it's really flammable. Back in the early days of surgery without, either, knocking you over the head or here, drink a fifth of something or other, they used to, at one point in time, build all these surgical suites of hospitals on the top floor. Okay, think about this. You have a potentially burnable, potentially explosive substance that you're using to render somebody unconscious. Well, oops, what if there's a spark? This is, granted, they don't really do this anymore, but if you actually visit some of the much older hospitals in some of the big cities, some of them still tend to locate almost by habit rather than intention anymore, put their surgical suites on the top floor of the hospital. This is a leftover from, what if the gas that you were using, what if the liquid that turns into a gas explodes? Well, you don't want patients above the explosion. Now, when you're making ethers, sometimes they match and sometimes they don't. So look at the one there that's labeled methyl ethyl ether. The left-hand side is different from the right-hand side. Ethers do not have to have matching R groups on the left versus the right. How about methyl T-butyl ether, which is the bottom left-hand one there? We've got a single CH3, but then we've got that kind of spoked, almost a plus sign looking thing there on the right-hand side. You can also use benzene groups, okay? In the world of common naming for organic stuff, they don't call it benzene, they call it phenyl. PHENYL. So diphenyl ether has one atom of oxygen in the middle and a benzene ring on each side. The IUPAC name that's written there below, though, phenoxybenzene, is more the IUPAC name. But lots of organic chemists just simply call it diphenyl ether. So there are some more yet to go. We've got another handful of organic functional groups yet to go, but this kind of gets us a bit further in our chapter here, and we'll end up finishing it up on Tuesday, probably. Obviously, the entire file has already been loaded. You will also see some other things that are loaded in the section that's called useful handouts. There is a PDF, actually, no, I think it's a JPEG, that is all the functional groups listed on a single page. You may want to, you definitely should download it. You might want to print it. It's a really, really useful way to kind of show you all the information in one go. There's also a other handout, which I think is a PDF, which is about naming. And I think there's an additional one also that I loaded up there. Flipping back and forth sometimes between all these different documents digitally is really kind of a pain in the butt. Questions about the organic stuff that we have covered so far?
You said most of this stuff was in chapter 20.
Yes. The isomer stuff is not in your textbook. So most of it is here in the notes, with the exception of my one example about the handedness thing. Okay, that's just a little smidge of information. all the rest of the stuff, all the functional groups, all the naming rules are also in your textbook, but the isomer stuff isn't. They don't really talk about the isomers there.
Okay,
Hence why we're trying to go over this in relative detail. And as I said, okay, next week's lab is all about using Excel, but the following week's lab, and I know that there's no lab schedule up yet, I got a batch of info from Mr. Wheaton and Dr. McHugh, but that information did not contain a schedule. So I am still punting a little bit on what exactly is happening after the next 2 weeks. I'm really hoping that they get this figured out fairly soon because I'd like to be able to pass the information along. But next week's lab is Zoom for everybody, no matter what lab section you have. We are all doing the Excel usage lab. And then after that, there is another one that is a Zoom that is all about the organic molecules. Only once we get to, I think it's the first week of February. Then there's going to be some actually face-to-face labs. And I think it's going to be spectroscopy, but I'm not sure. Other questions? You also might want to begin to look at the homework set for organic. It's not due yet. We have to finish the chapter before it's due, but definitely download it, have a peek at it. We have covered some of the information that is dealt with in the homework set. This is the one that unless you have a really grand and glorious computer that allows you to like draw kind of like my whiteboard on your document, you're probably going to have to print this homework set out, do all the pictures, and then take a picture to turn into a PDF in order to be able to load it back to the Canvas system. And I know I talked to somebody about Google Documents and PDFs, and yes, I found out for sure that yes, Google Docs will allow you to save your document as a PDF version. Should be no problems with that. And somebody also asked me about Chromebook problems that I still have no answer for. Supposedly, there might be a workaround for the Chromebook thing, but I'm not sure. It has to do with the fact that the operating system for Chromebooks is more like a cell phone than it is a computer. You can tell I'm not a programmer. So I know that it has to do with the operating system. So I'm still working on the whole Chromebook problem. Questions? Otherwise,
I don't know if there's anybody else who has a Chromebook, but I actually just bought another laptop, so I'm okay.
Okay. So yeah, it's like, you know, I know it puts people in awkward situations because, okay, my slight off topic. Last night, my son, who is taking physics from the beach camp, from the beach campus, obviously he's Zooming too. Last night is like going, he's been having computer problems for a couple of months now. And I hear him talking to my daughter going, I don't think it's supposed to smell like that. Why does it sound like a kazoo? And I'm like going, oh yeah, this doesn't sound good. So yeah, computer problems are expensive. Other questions? Otherwise, I will see you on Tuesday here. Well, on Zoom. I don't know if it'll be here or I'll be back in my office again. Bye.
Thank you.